Hi there and welcome to this video for Senior Physics on Electromagnetism and Electricity. In this video we're going to explore what happens with respect to a magnetic field as it flows through a current carrying wire and how these current carrying wires can then be converted into something called a solenoid to enhance the amount of magnetic field which is actually generated. Okay, so let's start off with the fundamentals. The key thing to understand is that any charge that moves will generate a magnetic field. That is probably one of the most fundamental concepts that basically is going to be employed throughout the whole of electromagnetism. Now remember, when we're talking about a charge, we're talking generally about the electrons. The electrons are negatively charged. If we have a current, then the charge is thus moving, because remember, current is the flow of charge per second through a circuit. So if we get a charge which is moving, it is going to generate a magnetic field. Now the first thing that we need to understand is that magnetic field is basically going to be perpendicular to the motion of that current, i.e. it's going to be at 90 degrees. So if the current is flowing at this direction here, then the result is that we're going to get the magnetic field which is going to be formed at 90 degrees to that motion. So if you have a look at the diagram to the left hand side here, what you've got is a board where you've got a wire flowing through the board, and a current is then flowing through the wire. There are then little charm compasses which basically will react to the formation of that current. The result is that all of those needles will move, and as a result they will produce concentric circles. So basically that will link directly to the 90 degrees, because if you think about the board is at 90 degrees to the current carrying wire. The compass will basically follow those magnetic field lines as it goes around that wire. Now also, if we increase the increase the current, we're also going to increase the magnetic field. Well, that stands to reason. If we go back to our initial statement, any charge that moves generates a magnetic field. It stands to reason the more charge we've got, then the more movement we've got. The more movement we've got, the result is we've got more magnetic field which is going to be generated. Now, as you know, putting more current through a wire is not a good thing, because that's going to increase the resistance, increase the temperature, and the result is that could result in fires. So we need to have another way of actually increasing the magnetic field which is generated by this current carrying wire. Okay, so let's have a look at the features of a magnetic field through a current carrying wire. I've dealt with the first bullet point, which basically is that circular concentric circles of magnetic field will be generated, which act at 90 degrees to the flow of current. Also, the further out that you go from the current carrying wire, the result is that your magnetic field is going to decrease. That again stands to reason, because you're less subjected to that flow of charge. Also, if we change the direction of the current, then it stands to reason that the field is going to change. And we talked about that when we looked at the Earth, and the idea that the Earth's poles can actually flip every 100,000 years or so. And if they flip every 100,000 years, the result is the magnetic field will flip every 100,000 years. And remember, we said that we had evidence of that in the rocks, where the iron in the molten rocks was able to flip and orientate with respect to the electrons, and so banding patterns are formed across the Atlantic Ocean. Also, the strength of the magnetic field is proportional to the strength of the current. You increase the current, hence you're going to increase the magnetic field. So I hope that gives you an overview as to the idea of what happens when we get a current flowing through a wire and the magnetic field that's going to be produced. Okay, so really what we now need to be able to do is have a way of determining the direction of those those concentric circles within the magnetic field, because that's going to be really important when we start interacting with two different magnetic fields, one from a magnet and one from some wires. And you'll see the relevance of this as you move through the course. Well, this is really, really good in that we have a help. We have hands. Now, physics or physicists in their wisdom have come up with different ways to determine the direction of magnetic fields and forces using our hands. Now, the first one we're going to learn is the right-hand grip rule. Now, in order to understand the right-hand grip rule, it's very, very straightforward. You imagine that you are gripping something. Your thumb is going to be the direction of the current, and your fingers, as they grip, are going to show the direction of the concentric circles working at 90 degrees. Now, let's look at the scenario that we've got on the left-hand side there. So you can see you've got a current carrying wire, and in the diagram, we've got a hand holding the wire. The thumb is showing the direction of the current flow. So you may be shown that direction of the current flow, or you will be shown with a battery that the battery is going from negative to positive. As a result, going upwards is basically, in this diagram, going to be our current flow, so that's our thumb. Our fingers are showing the direction of the magnetic field line. Now in this case, they will be going anti-clockwise. They're going from left to right as we look at it. So try it now and try and just see your pattern. Current going up and your concentric circles going around. Now, if we wanted to show this going across the page in the diagram just below on the right hand side, we need to have a way of showing in and out of the page with respect to our field lines. And this is where the second diagram on the left hand side at the bottom will show this. Now you can see here that basically we've got some circles with the arrows. Now they're going to show your magnetic field lines, but in the center you've got some circles. One's got a cross in it and one's got a dot. Now a dot basically denotes that the current in this case is going to be flowing out of the page. Now the way I explain it to my students, it's like using a bow and arrow. Somebody fires an arrow at you, what you actually see is the dot of the arrow coming straight out at you. So what you see is the point of the arrow. Now that's coming straight out of the page at you, so hence when you look on the left hand side of that bottom diagram, the current must be coming out of the page because the point is coming straight towards you. However, if you've got the current going into the page, it's like the arrow going away from you. And as you see an arrow going away from you, what you see is the flight moving away. So you get to see the cross. You don't see the point because the point is behind the flight. So point is coming out towards you, cross is coming away from you. So that's how we denote whether it's going into the page, cross, or coming out of the page, point. So let's look at our diagram on the right hand side. We've got a current now which is flowing from left to right. So work with me. We're going to put our thumb in the direction of the current, and as a result, as the fingers move, we're going into the page on the bottom and we're coming out of the page on the right. Now sometimes you're going to have to work it out. You often find yourself working around. Now the key thing to understand is you can take this into the exam with you. So if you can learn that the right hand grip rule for a current carrying wire tells you the magnetic field, you're sweet as. Okay, so also what do we say? It stands to reason that the stronger the current, the greater the field. And as the field is denoted by concentric circles of R, we then got, as we go further away, we're going to increase the actual radius. So the result is we would expect the magnetic field strength to decrease. So there's a calculation that we can utilize. Now the calculation is B, the magnetic field strength in Tesla, equals our magnetic constant, which is 2 times 10 to the negative 7 newtons per amp squared, times the current divided by the radius in meters. Now the magnetic constant will be given to you in an exam. You wouldn't be expected to actually remember it. Okay, but basically what it's working on is the principle that the further that you go away from the wire, you're going to find that your magnetic field strength will decrease. Now that comes from an equation between magnetic field strength and radius. If you plot this on the graph, you're going to actually get a straight line. The result of that straight line will basically be denoted by the gradient. The gradient will be the magnetic constant. Now what you will plot really is magnetic field strength against current over R, because remember, if you increase the current, you increase the magnetic field strength. If you increase the radius, you decrease the magnetic field strength. If you solve them all together and plot them, you'll get a straight line. B, I over R, straight line, which means that the gradient will be the magnetic constant. That's how it's calculated. Okay, so below we've got an example as to how we can utilize these two magnetic field strengths. So we're going to consider the diagram opposite. In the diagram, we've got two separate wires in close proximity, wire A and wire B. Wire A carries a current of 1.5 amps and wire B carries a current of 2.5 amps. We're going to calculate the value of the magnetic field strength at point X, which is between the two wires. Point X is 0.15 meters below wire A and 0.1 meters above wire B. So we're going to work out what that magnetic field strength is. Now what's going to happen is we're going to get some interaction between the two wires. Now the first thing we need to sort of understand is we can use our right hand grip rule for each wire. So if we look at wire A, we use a right hand grip rule. It's going into the page at the bottom of the wire. It's coming out of the page at the top. So just try that now and see if you can see that scenario. Then look at wire B. The magnetic field will be going into the page at the bottom of wire B and coming out of the page at the top of wire B. So at point X, what we'll be having is that we'll be having the magnetic field for wire B coming out of the page, whereas for wire A, it's going to be into the page. We've got two different directions. So the result is if we've got two different directions, we're going to have to make one direction positive and the other direction negative. Now that's going to be useful to find the net magnetic field strength between the two. So let's see how we solve it. So what we're going to do first is we're going to work out the magnetic field strength at point X for wire A. So remember, we know our current, which is 1.5. We know what our magnetic constant is, which is 2 times 10 to the negative 7. And we know what our radius is because it's at 0.15 meters from wire A. So we can put that into the equation, and the result is that we get 2.10 to the negative 6 Tesla, and it's going into the page. So then we do exactly the same for coming out of the page, which is going to be wire B at point X. We again know our magnetic constant, which is 2 times 10 to the negative 7. We know that our current at this point is 2.5 meters, and we know that we're 0.1 meters away from the wire, so our radius is 0.1. So as a result, we get 5 times 10 to the negative 6 Tesla coming out of the page. Now to work out the net magnetic field strength, what we're going to have to do is combine these two. And because they're going in opposite directions, the result is we're going to have to take them away. So basically what we're going to say is the total magnetic field strength will be the field strength of wire A plus the field strength of wire B. And if we choose out of the page as being positive, then we get the following situation. So remember that the field strength at wire A is going into the page, hence it's negative. Coming out of the page is positive, which is going to be wire B, which is 5 times 10 to the negative 6. So the result is our overall charge will be 3 times 10 to the negative 6 Tesla, and it will be coming out of the page. It's a vector. Okay, well I hope you found that bit useful. That's quite a complicated question where you have to use the ability to think in vector terms. However, the actual mathematical calculation is fairly straightforward, just using the normal equation. Now the question then is, how do we actually start to increase the magnetic field strength? Well, we can increase the magnetic field strength by increasing the number of turns of a wire. Okay, a single wire will generate only a small amount of magnetic field. We could increase the current, but we've already stated that increasing the current isn't a good idea. So if we coil it, what happens is the magnetic fields combine together. Now once we start coiling a wire, it ceases to become a wire as such, and we start calling it a solenoid. And what a solenoid manages to do is use a low current, but allows you to increase or combine all of the magnetic fields together. Hence you increase the magnetic field. So basically, you just need to understand that a solenoid is a coil of wire where all of the magnetic fields combine together to make a stronger field. Now this can be calculated with the following formula again. B equals 2 pi K N I over L. 2 pi is related to the circumference of the solenoid. K is your magnetic field strength. N is going to be the number of turns that you've got of wire, because obviously every turn that you get, you increase the magnetic field strength a bit further. I, obviously we know that B and I, you increase I, you're going to increase B. And obviously the length of the solenoid, the longer it's going to be, the less of a field strength you're going to get. So if you can actually make your field nice and close together, all the wires compact on each other, the result is you're going to get a really, really strong field. Okay, so we can increase the strength of the solenoid in the following ways. We can increase the number of coils, so put more coils on, and you can see straight away if you substitute that into the equation, you're going to increase the field strength. We can increase the current, and we've already stated that increasing the current is not a good idea because obviously you're going to generate more resistance. Resistance generates heat. Heat can cause a fire. Now the other thing that we can do to actually increase the field strength of a solenoid is to add an iron core. What adding an iron core does is enhances that magnetism by orientating the electrons inside the iron, and hence you become an electromagnet. And you can switch that iron core on and off as you basically turn the current on and off. And what it does, it concentrates all those lines of force and really generates a really good electric field. It's the sort of thing that you get in a car yard, scrap metal car yard. You see it on a crane, and basically they've got a large electromagnet which basically picks up the car and moves them around. Okay, now with respect to a solenoid, the right-hand grip rule can also be useful to us again. In this case, the thumb is going to show you the magnetic field direction, whereas your fingers are going to show you the current direction. Because remember, the solenoid is a coil. So the fingers are going to be our current, and our thumb is basically going to show us our direction of the field. Now remember, north on a magnet always has the field lines coming out. So your thumb will also generate or tell you that that is the north end of your solenoid. You always find that north will be running anti-clockwise and south will be running clockwise in this situation. Okay, well I hope that you found that useful. What I'd suggest that you go on and have a look at now is the other video in this post, which is using FET, and I go through the idea of the field lines with a solenoid in a little bit more detail. There's also a worksheet for you to have a go at, and there's a variety of questions there with the answers. So download the PDF, have a go at those questions and see how you go. Well, thank you for joining me, and I look forward to seeing you again.